Okay, assalamualaikum warahmatullahi wabarakatuh. Let me introduce myself. My name is Robi Harahap, and in this video I'm going to be explaining about optimization problem in numerical methods. So the problem here is a process of optimizing an airfoil shape for maximizing the lift to drag ratio using numerical methods in Python. So before we discuss about this, we need to know first about airfoils and how airfoils generate lift. So what is lift? When fluid flows past an object, the fluid exerts a force on the object, which can be split into two components. Drag, which is acting in the same direction as the fluid flow, which is this one, the yellow one is drag, and lift acting perpendicular to the flow direction. So this is the graph here. Lift producing airfoils can obviously be found in airplane wings, but also in many other applications like wind turbine blades or propeller blades. They're also used in the wings of Formula 1 cars, which are designed to generate downforce so that corners can be taken at high speeds. So even though they're just airfoils, they have different purposes. So one is to generate lift and one is to generate downforce. So the typical pressure distribution looks something like this one. On top there's a low pressure zone because there is a velocity increase. So as we all know, the increase in velocity occurs when there is a low pressure zone. So velocity is reversely proportional to pressure. So the pressure is low above the airfoil and high below it, which creates a net force with a large component in the left direction. If we plot the pressure profile on the top and bottom surfaces, we can see that the low pressure on the top surface is larger in magnitude than the high pressure on the bottom surfaces. So the suction pressure on the top surfaces contributes most to the total lift. So the suction pressure on the top surface is what contributes. So first, we're gonna use the DAI5 framework, which is the intention, initial thinking, idealization, and instruction. Intention to optimize the airfoil shape to maximize its lift to drag ratio, which is crucial for efficient aerodynamic performance, and to align this effort with the broader goal of becoming a better engineer and a servant of Allah by appreciating the complexity and beautiful of aerodynamics. Secondly, the initial thinking. What are the variables? So here, the airfoil shape is the variable, the lift and drag forces are the variable, and the objective function is the lift and to drag ratio that needs to be maximized. And the constraints, what constrains us from reaching our maximum potential? The airfoil shape must remain physically realistic, so we can't. This is a rule of thumb, and computational efficiency is important to ensure optimization process is practical. Okay, what are the idealizations, what are the assumptions, and how can we model this? So simplified calculations for lift and drag forces, assuming it's steady and incompressible flow. I may be wrong with this. It should be compressible, given that we're talking about gas particles instead of fluids. The airfoil shape can be effectively represented using a set of control points. And modeling define the airfoil shape using a cosine series representation, use numerical differentiation to estimate gradients. So we're gonna be what we're gonna see after this slide is I'm going to show you guys what it looks like in Python. Let me just open PyCharm real quick. So here, wait, it's not showing. Let me just do that for you guys. Sorry, that's not how it works. Sorry. Let me just do this. Yes, that's it. Okay, so you guys can see. Okay, so from the lines, wait, I can't really see. just go up. Okay, so firstly, there's got to be, it's essential to have import numpy, as it's a library for um, mathematical resources in Python. And nextly is matplotlib. When you want to make a graph or a plot, or to plot something, we can use matplotlib. Matplotlib, it's a useful library as well. Okay, so firstly we have to define the airfoil shape as a function of parameters. So, um, so x equals np linspace 0, 1, 100 is the steps that we're going to take. So this basically means that the x coordinates are evenly spaced between 0 and 1. And y np0 because we have to initialize y coordinates to 0 basically. And for I parameters and enumerate parameters, that line is obligated to modify y coordinates based on parameters using cosine functions. And we have to define how to calculate lift drag. So the simplified calculation of lift as the area under the curve of y. So we can use np trapezoidal yx, and the simplified calculation of drag is an integral of y squared. So we can use n trapezoidal y squared. So lift to drag ratio, we can define it to avoid division by 0 by checking if drag is non-zero. So we can check there in the line return lift drag, we can check if the drag is non-zero or 0, you know. And gradient is an algorithm. Yes, this is just an algorithm, and this is a small perturbation. We can define the main lobby basically, and this is just plotted using plotlib. So if we run this real quick, sorry, that's not the one that I'm trying to run. If we run this real quick, we should get a graph. I don't know if it's showing. Let me just okay. Oh my god. Let me just show you guys the graph real quick. Okay, can you guys see that? Can you guys see it? Okay, there's the graph. So as you can see here, the graph, it's a double curve graph. So once it reaches minus 3.0, it reaches the first peak, which is in the 0.2, 0.3 range, and then once it reaches the y-axis of minus 2.4-ish, it reaches an x-axis of 0.8. So the blue line is the initial airfoil, which cannot be seen here, and the orange line is the optimized airfoil that we just created seconds ago. So let me just show you guys my face real quick. So that's probably it for our explanation, our explained slash deconstructed problem for optimization regarding airfoils and how to optimize it in airplane. So if there is any questions, you can probably write it down in the comments below. I'm sorry if there's anything wrong in my explanation. Thank you guys. Assalamualaikum warahmatullahi wabarakatuh.